Our next presentation is from IBM. We have three speakers, Mr. Sudhakar Reddy, who is an engineering manager at IBM, Ms. Robona Mitra, staff R&D engineer, and Mr. Pradeep Kumar Nalla from the EDA formal tools and methodology team. I'll just give a quick intro. Sudhakar has more than 15 years of experience in the industry in various domains, spread over GPUs, CPUs, and the majority of his work has been in functional verification. I believe he has been using formal also quite extensively. He did his master's from IIT Madras in microelectronics. Shobona has 2+ years experience with the India Systems and Technology Laboratory at IBM. She has been with IBM since 2012, and she has done her MTech and PhD from IIT Kharagpur. Her PhD was on formal methods for aiding verification of local design changes in digital integrated circuits. Mr. Pradeep Kumar has more than 6 years of experience in VLSI. He has been involved in the development and support for the formal verification tool 6th Sense, and he has also been with Atrenta. He has done his PhD from the University of Tübingen, Germany in 2008 on efficient distributed bounded property checking. I'll hand it over to the presenters from IBM.
Good morning, all of you. I think many of us know each other. So let us keep this presentation or discussion interactive. The key takeaways from this meeting I would like to see this forum is, now what are our experiences from the formal verification adoption within IBM designs. So IBM, as you know, has been in the industry for so many long years, especially working on the enterprise processors. So in the industry, you might be hearing about PowerPC and System Z processor, System Z which goes into mainframes, and PowerPC which goes into mid and low-end servers, right? Apart from that one, we also have ASIC teams. So the formal verification team within IBM, as Kiran told, I've been with Intel also, I've seen formal going there as well. So this team's charter is to grow the adoption within IBM design. So I'll take you through the journey of how we have done it within IBM, and some recommendations for the formal community so that the adaptation will be widespread. Can you go to the next slide? Yeah. So my colleagues will take you to the through the second part and the third part. What I would like to point out here is, within IBM we have advantage of having EDA team which develops the formal verification tools and the methodologies. Plus we also have, as you know, both designers and verification guys who are helping us in adopting these tools, right? So I clearly see the advantage having these two teams working together. And in any industry or in any company, we all know that the in-house tools have the competitive advantage also in terms of customizing these tools for the internal requirements of this design, right? In this case, it is mostly related to the process. Okay, so this slide I have taken it from the recently concluded DAC conference. Putting the things in perspective, as you can see, even across the industry, we can see that the new markets, new areas where they are focusing on selling the tools, is one of them is formal verification. You can see the adoption growing and the revenues increasing in the formal verification also. So IBM is no different. IBM has been in this formal verification for the last 20 years, if I remember correctly, and many experts working only on these formal engines, both in model checking and equivalence checking. All right, and yeah, that is one thing I wanted to point out here, right? I would like to quickly share my story today when I am coming from my house to Cadence office here. Couple of years back, few years back, I used to work in Intel, right? And that time, you know how the outer ring road was there, looks like, right? In 2005, 2006 time. That time I used to come by two-wheeler, right? And then I used to take only 20 minutes to reach from Bagmani Techport to Intel office. So today when I'm driving on the same road, all right, but shifted to four-wheeler, it took me almost 45 minutes. Okay, so when I relate the same thing to my design community here, the size increased and complexity increased, but my tool didn't help me to meet the same timing here, right? So that is where I would like to put the formal tool in perspective, in complementary to the existing simulation tool. So our job is to not to challenge, say, we will take over everything end to end. That is not the right statement here. In my experience, at this, when I see the maturity of the tools, even in-house, but we go with a mindset that, okay, we are here to help you out in speeding up your closure and verification, right? So that is the main motivation here, right? So apart from that one, I have few questions to this community to help out in adoption, right? So how many of us really put efforts to go back to the designers or leads and asking them to involve us early in the project planning or test planning? How many of us seriously think about it, right? How many of us seriously put efforts on that? When we have put those efforts, we have seen the results coming out of it. Okay. We also need to take into account that identifying the blocks which are suitable for your formal verification, right? That is the first thing to start with. And the second thing is, sometimes formal verification guys, if they had not worked on the design, they would not know the complexity of the design and the internals of the design. You would definitely need the help of designers in terms of getting the internal details, signals to attach, because these are all helpful when you are coming out with the properties and assumptions. All right. Unless you have those details, it is not an efficient way of deploying this formal verification tool. And the third one is accounting your time also spent on this one, right? So what needs to be done, where it needs to be applied, and how much effort you need to put in, right? So I don't know how many of you know. Now there are there is one company which I know is fully focusing on consulting for formal verification. Have you heard about that company? Right? So now you can see the focus that is shifting towards formal verification, right? So I can take that name. It is OSKI, OSKI, so which is I think spun off from some other company. They are fully focusing only on consulting for formal verification. They'll come to your companies, analyze your designs, and recommend the tools and methodologies for that. All right. So that is the focus that formal is getting nowadays. All right. And also don't forget that formal also needs some time to develop environment. If it is, if you are doing it for the first time, right? What I mean by formal environment, you need a driver to drive your stimulus, you need checkers end to end, all right, and you need to develop the properties, all right. So, and then verify and then review the code also. We do robust reviews with very detailed reviews with the designers to make sure all the properties that we have written are not over constrained or under constrained. All these things, right? Okay, so those are my my experiences as a manager, as a lead in the past. Some of the challenges are still open. Shrobana and Pradeep will take you through. Pradeep will take you through from the tools and methodology standpoint, and Shrobana will take you through the application standpoint, right? So we are here to help you out to take away some learnings from this forum and apply to your designs also. Okay, thank you.
Yeah. So as Sudhakar mentioned, I will brief on the our in-house tool 6sense, rule-based 6sense. Yeah, I mean the main advantage also I see in IBM is that like work closely with the execution teams. I mean that's a good opportunity, and also you work on the real-time problems. What are their needs, and then you work on more reactive and proactive manner. Right. I mean yeah, this slide is a very basic. Everybody knows this. Even today, the conventional method we use is the simulation, and then there is no completely replace that one with the formal. People don't agree, and then also it's limitations with the formal as well, right? So of course, like why we go formal, we had enough stories from Kiran, and then also as Sudhakar mentioned, right? I mean, Intel floating point bug and then all that, right? I mean, it can cover conventional bugs. But apart from these simulation and formal verification, what is also very much important is the semi-formal verification, right? I mean, so the limitations of the formal, it cannot go much deeper. It can throw like it can cover breadth, and then it can find corner case bugs. But what happens if my bug is very far from the initial state, or at least you need thousands of cycles to reach there. The best solution is that like apply semi-formal verification, right? I mean, the idea is that like you apply simulations for quite a lot of time and then pick some interesting states. I mean, one heuristic could be that like, this is the rarest state I have visited, and any heuristic which is of importance, right? And then, start formal verification at least locally from that perspective for some time. And then if you don't get it, again, you switch back to simulation and then do this iteratively. So, and this is very much of important as well, at least to handle the scalability. Okay, this is again from the tool standpoint, like over the time, like in the late 1980s, right? So we started with the explicit state model checking. So there, like the FE was very much like the designs of 100 or 200 state variables. So now it reached to a point that like at least it can handle larger scale designs, like several 100,000. So starting with explicit and DDD, and then SAT solving, and then bounded model checking, then later inventions with the transformation-based verification, which we brief on that, interpolation, and then now property-directed reachability. Of course, like as I said, all these, but there are even tinier problems like which formal cannot, have full proof. For example, arithmetic logic, right? Like having full proof is almost a dream here. Okay, so the evaluation at IBM. So it started in 1996. Formal was started the deployment, but as an experimental basis. Okay, but that time only it was applied for the logics of relatively smaller size, control logic, and so on. And then this was applied on Power 3 processor at that time. And then more defined manner also on Power 4 strategy processor. And then moving on, like actually the main the transformation based verification, the handling scalability, and the semi-formal verification, the invention of all these actually made formal to apply more logics and then more blocks, right? And then going forward, like in 2006 time frame, like a Power 7, it was a mandate for IBM to actually many of the core units actually verify through formal. So in future, we want to see where like the formal, how can we efficiently reuse the already existing information from this, the simulation environments and so on. And one other key the success story is also the deployment of the sequential equivalence checking, as Kiran also mentioned, right, RTL to RTL. So this is a very much also important for us as well. Okay, so this is the verification flow at IBM. The main essence of the flow, is the actually call it as a cycle-based execution model, and then we see, right, like the tools, internal tools from IBM. One is the software simulator MESA we call, and also the hardware accelerator and then emulator and the formal verification. So they all work on this common execution model. So this is common for all verification disciplines we use. So as I said, like one advantage is also is the reusability. The environment or the verification objectives we construct, like assumptions and then assertions and so on. So those can be reusable across different disciplines. Yes. Yes. Okay. So yeah, this is the big picture. Wherever where we apply formal, starting with the block level and then unit level, element level. of course, not necessarily like we completely include all these and then do the verification, but a lot of abstractions and then behavioral models we use and so on. So our colleague Shobana will brief on the execution aspect of this. Like she will revisit this slide in more detail. Okay, I will brief on this tool aspect. This is very much self-explanatory. Like we call this rule-based 6 sense in-house tool. Yeah, so we take the design like VHDL, Verilog, and Next Verilog and VHDL, and then specification in PSL. And then in addition to PSL, we also support like it's extension of actually VHDL. We call it as a bug spray. It is internal, IBM internal, and also system Verilog assertions to some extent. And then yeah, so we get a fail is a counterexample you get, and then pass. And so you also optionally get a witness. And then we also reason more whether it's a pass means like it's a backwards pass, right? And then it's a bounded pass. So again, going back to the Kiran's point, right? Like what management asks, like where are you? I mean, you don't get the result, right? So we can also claim some of the bounded reasoning, right? That these many simulation cycles, if we cover completely formal, so that kind of reasoning also we can mention. So other aspect is the the sequential transformations are widespread across our design flows and hierarchy. For example, the clock gating and then power and then the timing and then logic optimization and all those, right? I mean, so therefore, like for all to verify all this, like a combination equivalence checking is not sufficient. So there, like it expects to have 1:1 state element pairings. So we need a sequential equivalence checking tool. So IBM has an in-house sequential equivalence checking which can handle the very big designs. Right.
Just to add to the project standpoint of like everybody who are working on design, typically in internal and IBM, we have multiple specifications, right? So when you are transferring your design from one setting to other setting, next setting is generally your fine-tuning of the design. Okay? So sequence equivalent checking has helped us in reducing the time in making sure the functionality is not broken because of those optimizations. Right? So that is the advantage that we see when we verify the same design but within the two specific. So that's one thing that we are applying on.
Yes, exactly. That is the same thing. Like yeah, as you said, like when we are reaching to the later stages of the design cycle, and what we do is that like we check at the macro level and then we perform the SEC and then we do black boxing and then reach a higher level slowly.
So we have a big saying that formal is applicable only at unit level, only at macro level. I think we have gone far due to the improvements in the algorithms and tools, advancements in the tools. So now we are able to do mostly at the block level and the macro level, but we are also moving at the block level and then to some extent this level with the semi-formal as well as black boxing and hierarchical.
That's right. Oh, okay. Yeah. Okay. Let me first brief on this slide first. Actually, okay. So our methodology works on it's called a transformation based verification. Okay, let's assume that like this is your design characteristics, like you have a design and then driving logic and also checking logic. So this has around 140,000 registers. So what we do is that actually, we do a lot of logic optimizations engines first. Okay, so try to simplify the problem or remove the redundancy and so on. That actually significantly can reduce your design size. And then further, like you can apply all the further, like this is a phase abstraction engine, like we call modulo phase folding engine. So it can further, I mean, if your design is not sensitive to clock and so on, right? Like it can further simplify the problem. And then at some point you can reach to a place where like you can apply core algorithms. Okay. So for example, here you can apply semi-formal engine or the proof engine or the abstraction engine. Okay, so so these can be applied parallelly or the sequentially. Okay, so assume that like this is the direction is actually that is actually we are not finding any bugs. So let's go in that direction. I mean, so let's go towards the proof, right? Like if the abstraction is doing good job, so what we do is that like then we discard the other engines and then go with the on the abstracted model, and then try to prove with the again semi-formal or the interpolation or the proof engine or the retiming engine, and so on. So this is how it was the transformation based verification. So if in this actually any of the place like we find a trace, right? So what we do is that like we can always list the trace until it can be represented only in the form of design signals. So this way, these actually results are completely transparent to the user and also enable the exponential speedups. Yes. Yes. Yeah. So this is localization engine is actually the abstraction engine. So it, yeah, I mean I will brief on the next slide actually. Yep. So I will go back to yeah. So these are the various engines we have in Sixth Sense. So these are actually categorized under we say various, like some are good for proof and some are good for bug hunting and some are good for only for simplifying the problem. We call a transformation engine, and then some are like good for now. Shobhana will talk like so far like possibly you check more on safety properties, but there are liveness properties also very much important. So now we have large, I mean, at least 5 to 6 engines that actually targets the liveness verification. Okay. So in addition to all these engines, actually what we also have is the expert system. So expert system, what it does is that like it tries to play with these engines, heuristically. Like if first let's say I apply this engine, so I observe these characteristics. So based on these characteristics, what I do is that this is the next set of engines I should apply. So based on that heuristics that we apply. So this is both like a sequentially we can apply and also parallelly. Yes, so same. We also apply for floating point and then the fixed point and all that. Same. Okay, yeah, these are the just to brief on the some of the engines. The retiming engine, so it tries to reduce the mean area by moving across the registers, and then redundancy removal. So a lot of the equivalence checking problems. So many of the internal points are actually equivalent. So we tries to find all those internal equivalent points automatically, and then the localization is the abstraction engine. So it actually tries to remove all the irrelevant logic for our target verification. And then finally, logic rewriting is actually the Boolean optimization engine. How efficiently I can rewrite this particular Boolean logic with some other so that I can reduce the area. And then so I mean the simple idea is that like simplify the problem as much as you can, and then apply only the core problem to handle the scalability and all that. Yeah, most of the times we try to be independent, but sometimes like if are hard to get full proofs and so on, like then of course like we need to take help from user, like can we break the property or can to do all the aspects. Okay, yeah, that's all I can. I will stop there and then I will handle the control to Shobhana. She will talk on the execution perspective.
Okay, so I'm going to talk about the application of formal verification on the IBM designs. So we revisit the picture that Pradeep showed some time back. These are the different levels at which we have applied formal verification within IBM. I'll go step by step. So the maximum use of formal verification happens, of course, at the block level. This, the advantage of the block level is that we have the controllability, that is we are able to drive at the interface and exercise most of the corner case scenarios, and it's easier to get a full proof because the logic size is very small. The examples would be any macro level, like state machines within a particular unit. Suppose in a cryptographic unit, small, any of the cryptographic engines, examples are blocks like that. We isolate that block out and we drive at its interface and we try to get a full proof of the properties there. It's basically targeted deep dive every. The main problem there is that documentation at the macro level is typically very less. So we are very dependent on the designers, what the kind of information they can give us in order to build the environment. So the unit level is the next level where we apply formal verification. Here the information that we have on the interface is much more, because the units are typically much more well defined, and the drivers and checkers that we develop are more reusable once we have them. We usually have complete end-to-end reference model based checks. For example, it's the floating point units, the fixed point units, any of these execution units where we usually apply this FV. And for the other units, we are still in the process of trying to get to the unit level. The element level and the chip level, these are the logic that we have to cover is typically big here. So we would make a very heavy use of abstractions, of black boxing, of having behavioral models for the different parts of the logic. And what we try to verify at this level are core unit interactions, then non-core units, the cache, etc., interactions between them, and also the pervasive logic, which is actually the chip bring up logic, like the clock distribution logic, the power management logic, the thermal units, units like that. We apply formal on them, as well as we have been applying sequential equivalence checking between the different versions of the design on those units. And we also have some protocol analysis, that is some, as I said, interaction between units. If there's a protocol we want to verify that, we would have behavioral models for the different units, and we would try to verify that internal logic for the protocol. And the other application at this level is recreating bring up fails. So if there are any fails at that level, we try to look at our the environments we already have, or we try to get a basic environment up and functioning, and we try to recreate the fail that is there in the taking the feedback from the fail that was seen, the scenarios that was seen. At the system level, it's basically used for inter-chip interaction verification. There, of course, we would have again abstractions or behavioral models for all the chip levels, and we would be verifying whether some register writes or some kind of interaction protocols are working properly in place or not. Yeah. So
just to add just to give you an idea, we also have a dedicated formal verification system. So this is developed along with the unit there, and we track them very closely on a daily basis and see the progress that we make. And what is the unique value addition from the formal also we make an analysis. Right? We also participate in market case analysis, and we try to see why it is rescued from the formal standpoint. If some environment needs to be tightened, we do that. Right? So I think it is more proactive participation from the formal team that we need to put in the initial stages till you get the buy-in. And once the designers and verification folks see the value, they will definitely adopt this methodology that we have seen in our own experience. Right? And also we have coverage mechanisms to track the progress even from the formal verification side. So we try to help in closing the verification of particular units, especially the new units where we have micro-architecture changes and design changes, to find the bugs that is the value addition, right? To find the bugs that is, and to find very complex ones because of the exhaustiveness of the formal verification. Right? So please keep this in your mind when you are approaching designers, right? That makes your job easier in getting there by.
How many coverage telling you progress of your?
Yeah, as Pradeep mentioned, right? We use the same methods, same birthday event. Outside world, they are known as similar assertion. So we take the same birthday assertion and we try to prove the coverage of them using formal methodology. Right? Okay. And during the process, if you find some good work, that is good. Right? Because of the exhaustive
experience to add that, right? Like, as you also said, right, we also define a lot of cover units, okay, to measure the where we are and so on. So, and also the boundary region that is also we try to make. And also, I know that like we have a lot of problems, we don't have any full proof, right? So the only way we tackle is the under approximation, like case switching, there should be some of the inputs and so on, and then try to do something. That's the only way.
And the other value addition operate we are saying is the post-silicon bugs that we are finding. And if we can help out in reproducing them quickly at the unit level, we could question that why you need to use this formula. That's a different story. Again, it goes back to using something in our context. Alright? But the essence there is reproducing that bug quickly at unit level where you have more control of the observability of the debuggability of the unit, right? So that's the
So in this slide, we are talking about the same thing, the quality refinement process. So every bug that is found at a higher level, even the bring up level, power on level, these will be considered as an escape of the lower level. This escapes normally happen because one thing, we do not have formal environments for each and every unit, of course, till now. And the other thing is that sometimes our environments might be over constrained. So we need these feedback from the bugs at the higher level in order to relax the environment more, so that we can actually support catching that bug. So basically, higher level bugs are used in order to tighten the environment for the lower level formal verification. So another main application that we have been doing recently of formal is in the liveness checks. So a liveness property is different from a safety property in that it asserts that something good will eventually happen. So let us take the example of this arbiter. It has an input request and it is supposed to give a grant to the requester. And our liveness property would say that every request should eventually get a grant. So these traces are normally of infinite length, the counter example, because it would show a trace where a request has come but no grant has come for a period of time. So simulation is actually inherently incapable of proving liveness. This is because that checking is ad hoc and it does not keep track of any of the visited states. It cannot keep track of that. So formal is suitable in that case both for counterexample finding as well as proof. And we actually have been able to find liveness bugs which were actual hangs in the system, which could not be caught in any way through simulation, but were caught through formal of that particular unit. So, but the problem is that for liveness checking, the model, whatever is the model size, it increases much more as compared to the safety property checking, and that is because we need to keep track of we need to keep duplicate shadow registers for tracking the visited state. So liveness is a desirable property to verify in this kind of applications. One is arbitration, as I already discussed. So another very important application we have been doing is for FSM. So we have many state machines in different units, and for each of them it is desirable to check that whether either a completion state or some kind of error state has been reached, and at no point, whatever be the inputs coming in, it does not go into a hang. The state machine does not get stalled in any intermediate state, which is the problem. So that is what we are checking here with liveness check. And we also, another very typical application is for the least recently used algorithm in the cache replacement policies. So there we need to check that every entry eventually does become LRU. So it's not that some entry is not becoming LRU in any time in the future. So these are the kind of checks we have been doing, and we have found quite a few hangs with the liveness checking. For full proof, we need to go back and forth with the EDA team, with Pradeep and all. And sometimes we might have to approximate the check with the bounded safety checking, because liveness, as I said, the model size often becomes too big and we are not able to get full proof in that case, and we try for bounded proof, where we check that this particular thing is not happening within some bound. So if we are able to get a proof, we are done. But if in that case we get a counter example, then that counter example might be false. And that is something we need to go with the designer and find out where if the counter example looks correct or not, maybe refine our model, go like that. So the main problems that we have been seeing in applying formal have been absence of detailed design documentation, which is very which is a very big problem we have to deal with, because most of our checking is at the macro level, as I mentioned. Getting designers bandwidth, because sometimes it's really difficult because they get caught up in other things and it's difficult to get the time, and without that it's very difficult to proceed at the macro level, because you do not really have any other source where you can go to. And every team is not involved during early phases of design verification, which becomes a problem, because when the fresh changes keep coming, that is when it would be most beneficial for us to come in and get the environment and start finding bugs at that stage. And we would also be able to demonstrate our value better at that point of time. But it often has happened that we have not been able to get in at that stage, and when we do come in, already a simulation has been running on those designs for a long time. So that is one thing that I have felt. If every team is involved from the early phases of design verification, it will really help. And we also, it's our objective to arrive at more formal verification packages or solutions. For example, a package for the clock gating verification or sequential redundancy identification in designs, and LRU, for LRU verification also we have some kind of IP where we have the checks as well as the test bench. So that is the kind of packs that we aim to have in order to enable better adoption of FD.
Then the designer came to us approach and asked me and Pradeep actually helped the designer in identifying a lot of redundancy logic which is lying in this legacy design. All right. So that has shown up a significant improvement in reducing the power. That's how the chip power, at least to some extent, we are able to contribute to the reduction of that one. So that is one application. Yes, dead code. Yeah.
Dead code, something.
Yeah. So which is just one application, or which we have done recently. And one more thing I would like to mention is, and a lot of companies will have a lot of projects running in parallel or sequentially, and leveraging what has been already worked in one project and reusing it in another project with a little bit customization also helps in adapting these tools pretty faster. Right? That's what we have seen between P process and G process. Some of the methodologies or functionalities are common. We try to maintain the same driver, checkers, environment also in the same manner, right, with a little bit customization.
I mean, yeah, the code is like, there are a lot of things like a lot of things, and they wanted to have. Okay, one is the cone of influence is very much simpler to catch, structural traversal and all that. So they want to also have stick at 0 or 1. Okay, they also want to have some signals. They will be sticked after some time, sticked with 1 or 0, but after some time. Let's say after 10 clock cycles, they will be sticked with 1 or 0. Okay, So that kind of the information they want. Like some are unobservable, right? Like some logic is there, so they want to have it. Yes, but here like you have a full proof that like a formal says that like it's so like a simulation maybe is under you may cover only a few parts, right? But not all the parts. Like here I say that like one is packet with 1 or 0 is proof. Okay. Yeah, just to conclude on the tool side, like we also constantly work on like scalability point of view, like how can we make FE to the next level, and also still the designs having memories to apply formal verification is still a dream, right? So how efficiently we can apply there, and then all that, like we are constantly working on them, even the efficient memory management and all that. Yeah. So and also apply SMT theories, satisfiability modulo theories, and formal verification. That's all. Yeah. Yes, I think. Yeah. Yeah. So one of the question is that like at a system level, like other than the connectivity checks, like we can do something more, right? So I think they did done that. They actually modeled in a multi higher level models, use some asynchronous, the traffic control thing. Like I don't know all those clear details, but some of our colleagues actually handled. The idea is that like they extracted the behavior model, manually, and then use some models, morphing models, and then check the asynchronous some traffic control and all that.
So that's more of architectural verification.
Yes, 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 yes. Exactly.
So I think if I understand this question correctly, he's asking like what do you do and the RTL is
right? Yeah, yeah, that.
Other than connectivity.
Yeah, that.
Can you throw some light on that? Mason and VAS
yes, and floating point.
I would recommend, especially for people who are working on process, go and refer to some of the papers that were presented recently. One of them is on the floating point.
Yeah, control flow verification of
That's a control flow.
Yes.
These are accessible.
Yes, these are accessible.